You're driving down the road one windy day when you notice a peculiar sign on the side. Being the excellent MEAM student you are, you immediately begin analyzing the situation. So what loads are acting on the sign? We have the weight of the sign itself, mg, which we'll assume is uniformly distributed, and the force from the wind, F sub w, which we'll also assume is uniform. First, consider the wind causing the sign to twist. As it blows, it generates a moment on the sign and causes the pole to be loaded in torsion since it's fixed to the ground. Take a look at the grid texture on the pole. Note that the squares deform as the sign twists about the y-axis. Next, consider the weight of the sign. We treat the sign as a uniform rectangular plate, so its weight can be resolved to a force acting in the negative y direction at its geometric center. Since this is offset from the axis of the pole, it creates a bending moment about the z-axis as well as an axial force along the axis of the pole. Finally, consider the wind blowing against the sign. The distributed load due to the wind can be resolved to a single force acting in the negative z direction at the sign's geometric center. Since the pole has height, it generates a bending moment about the x-axis as well as a transverse shear stress. Now that we know about all the loading conditions, we can apply the following equations to the system, treating the pole as a hollow cylinder with a thickness that is far smaller than its radius. We have four types of loading acting on the sign: axial, bending, torsion, and transverse shear. Pause the video and make sure you understand how each equation is obtained. Now that we have the right equations, we can draw the stress elements. Let's look at the 2D stress element taken from the front of the pole. We have shear stress tau sub tor from the wind twisting the pole about the base. Imagining this element on the pole itself, the wind pushing along the z-axis causes the top of the pole to twist counterclockwise. Similarly, the top part of our stress element will twist counterclockwise, so we need an arrow that corresponds to that movement. If we took this piece of 2D material, a counterclockwise twist causes the top of it to shear along the positive x direction, so we draw an arrow to the right along the top. We then draw an arrow in the opposite direction on the bottom to maintain force equilibrium. We can also represent the bending stress due to the wind force, sigma sub w, on this element. It causes the pole to bend backwards, putting this element in tension. However, the axial stress due to the sign's weight, sigma sub a, puts this element in compression, so we must take the difference of the two when calculating total stress. Lastly, to maintain moment equilibrium on the element, there must be internal shear stresses on the right and left sides to counter the couple moment generated by the torsional loading. Note that the transverse shear stress is 0 at this point. Now, consider a second 2D stress element taken from the left side of the pole. Again, we have torsion tau sub tor from the wind twisting the pole. However, we also have a maximum transverse shear stress at this point due to the wind force, so we must take the difference of tau sub tor and tau sub trans. Additionally, we now consider the bending stress due to the sign, sigma sub mg, instead of that due to the wind. This puts the element in tension. We also have the weight of the sign causing an axial stress that puts the element in compression, so we again take the difference of the two. Add the internal stresses to maintain equilibrium, and that's it. Here's what the sign might look like under extreme conditions.